the so I guess another way to think of it is that T contains all the information necessary to estimate theta. So let's just take a look at an example and you'll see what I mean. So if you have x1 to xn IID Poisson, okay, so here is the likelihood function, and as you can see, it's a function of theta and your data, and we're going to show that the sum of your data is a sufficient statistic. So now, to show that it's a sufficient statistic, we have to show that that the data conditional on t is not dependent on theta. So remember from Bayes' rule, the conditional density is written as the density for x1 to xn and t over the density for t, and of course this density x1 to xn t is only non-zero if t is actually the sum of x1 to xn. If t is not the sum of x1 to xn, then this is 0, and so we're not really going to concern ourselves with that case. But when t is the sum of x1 to xn, these particular x1 to xn that we have here, then t is just redundant, right? If you know x1 to xn, then you know the sum. So this numerator is just the density of x1 to xn. Oops. Okay, so this is a calculation. So we need to find the denominator here. So the density of t, because the xi's are Poisson and t is a sum of independent Poissons, is Poisson and theta, then we can write out the density just because so just following the formula for the density of Poisson. We have this, and so this is just awesome amazingness here. You can see that the numerator and the denominator have some massive calculation. In fact, all the theta stuff cancels. So in this sense, t, the density of t, contains all of the information about theta from your data. It just cancels out like this, and we're left with the conditional density not being dependent on theta. So that is the definition for t to be sufficient, and that's the end of the proof there. So just to make this a little bit more clear, you can ask, what's the chance of drawing 1, 3, 4 from Poisson lambda? Or I guess it's Poisson theta, sorry. Right? So the answer is, well, it's IID, so it's the product of these probabilities, so it's this, right? And well, I don't know what that is because I don't know what theta is, so I can't answer the question. However, if I ask what is the chance of getting 1, 3, 4, given that the sum of my draws is 8, well, this I can find because t is a sufficient statistic. So that's kind of cool, right? So we just calculated the density for the probability for 1, 3, 4 given t is 8 is It's this formula. It's this formula right here. So it's 8 factorial, 1 over 1 factorial, 3 factorial, 4 factorial, 3 to the power 8.043. I bet you didn't know that. That's cool. Okay, so a useful way to think about what a sufficient statistic is well, first of all, just a statistic partitions your outcome space. So like your x1 to xn. So basically, you can have many different values of x1 to xn that have the same that have the same value under the statistic, right? So like if the statistic is the sum, you can have a lot of numbers that sum to 5, for example. So your outcome space gets partitioned into those outcomes that have the same t value. Okay, so that's one thing to keep in mind. And so here's a good simple example to understand. So let's say that x1 to x3 is our Bernoulli, so this is just a flip of a coin, and t is the sum of the xi's. So we have 8 possible outcomes, and you can see that these 8 possible outcomes here are the values of the sum of the xi's, t, and you can see that it gives us partitioning. So we have a partitioning of 4 partitions here. And then we can see that t is sufficient because we can calculate what f of x1 to x3 given t is, whatever the t value is, that it's not going to have any dependence on theta. And so you can just check here, like for example, this second one here. So for this second one here, the numerator is the chance of getting 0, 0, 1, which is 1 minus theta times 1 minus theta times theta, divided by the chance of the sum being 1, which is, well, the sum being 1. So here are the 3 ways that they can sum to 1. So they're each 1 minus theta, 1 minus theta, theta. So you get a cancellation of all the theta stuff, and you just get 1/3. So hence t is sufficient here. So here's an example of a statistic that's not sufficient. So say that t is just the first entry, x1. So now you can partition your outcome space into 2 parts. And you can see right away, here that your conditional density here does depend on theta. So t is not sufficient. So that's all fine and good, but this seems like a lot of work to determine whether a statistic is sufficient. So what you'll usually be using is the factorization theorem, which says that t is sufficient exactly when the density factors as a function of only your data times the statistic and theta. So let's look at an example here. So let's say that I have x1 to xn Poisson theta. So this is the example we did before. So here, let's see how we can factor this so that we can see that the sum of xi is sufficient. Well, we can factor it like this. So here, h is a function of x1 to xn, and g is a function of t and theta, right? There are no x's in there. Thank you very much. Here's another example, a little more complicated. So you have x1 to xn IID normal, and we're going to look at a situation. We're going to look at a case where sigma is known. So we're looking for estimating just mu here. Now the density for our normal is this product, because they're IID. I just basically wrote this out some more, and honestly I don't see right off how we're going to factor this, because the xi minus mu are together here by this square, and so we need to separate them into separate functions, h and a g, because the g has the mu and the h has the x's. So we're going to do a trick. We're going to write the xi minus mu squared. So we're going to write this in a tricky way here, do some FOIL action. Notice that the cross term cancels, and so we have this, which now we can substitute in here, and we get this. So sigma squared is a constant because it's known, so you can think of it as like 5. So all this stuff here in the top here, this h of x stuff, only has x's in it, and the bottom, and the g here has t, which is x bar, and mu. There are no x's. Again, sigma squared is a constant, hence x bar is a sufficient statistic. Right, so for mu. Awesome. And so tying this together, corollary A on page 309 in Rice says that if t is sufficient for theta, then the MLE estimate is a function of t, right? And so that follows because so the factorization theorem says this, yet right, this is the part that has theta in it, right? And so what we do when we do an MLE estimate is we maximize this density likelihood function as a function of theta. So we find the theta that maximizes this, right? And hence and so to maximize our likelihood function here, all we need to do is find the theta that maximizes g of t theta, right? Because if we find the theta that maximizes the g part, then we'll find then that theta is going to maximize f, right? So only t is necessary from your data to determine theta. It's a beautiful thing. So your statistic is a much reduced data than x1 to xn. And so this does result in a big data reduction. So sufficient statistics are very important today because it allows, once you identify that you have a sufficient statistic, it allows you to reduce your data. And a natural question is, what is a minimal sufficient statistic? not